you're confronted with this. This algorithm, which you think you have very strong reasons to believe, is the universally true fundamental physical account of the evolution of the world, is giving you wildly wrong predictions about what happens in this simple case, where you go and look at the electron that starts out in a superposition of being here and here. Once again, the natural reaction, the reasonable reaction is, well, okay, it was a nice algorithm while it lasted, but something is obviously wrong, okay? And we're gonna have to change it, okay? We should probably try to figure out a way to change it that doesn't mess up any of the predictions it makes that we know to be good, okay? But change it in such a way that it doesn't make this crazy prediction about what kind of mental state I'm going to be in when I look at this object. That's what I would characterize as the natural, reasonable, scientific reaction to this. This was not the reaction of the founders of quantum mechanics, okay? And it was particularly not the reaction of Bohr, okay?
Yes.
Bohr thought...
The Church of Satan, as you famously referred to him last time.
I mean, I don't, as soon as I say the words Bohr thought, I have to pause because it's very hard. He is very, very far from expressing himself in a uniform and internally consistent way. But let me do the best I can. Bohr thought that this was not a scientific problem, okay? That you should not be fiddling around like a nerd, changing this part of the algorithm or that part of the algorithm to get everything worked out, okay? No, this is the childish reaction. This is the stupid reaction. This is the shallow reaction to what's going on here. Bohr thought that it was a deep mistake and that one of the great lessons of quantum mechanics is precisely that it was a deep mistake. To have this even to entertain this aspiration of throwing everything into the physical system that we treat with this algorithm. You remember that we said, okay, we have this electron that's in a superposition. Well, what happens if we hook it up to one of these detection devices with a pointer? And now we're going to play the game of assuming that the detection device is another ordinary physical system. That is, all we're doing here is really calculating the results of some kind of interaction between two physical systems, some kind of a collision between two physical systems. If we want to figure out what's going to happen to the needle, you just treat the needle as another physical system whose behavior in interaction with this electron is something covered by this universal algorithm that we have. You plug it in, you grind it out, you see what happens, but you get an answer you don't like, that the needle is going to be in a superposition of pointing this way and that way. Then you say, okay, you know what? Let's throw the observer into this physical system too. Let's treat the observer as yet another physical system that's interacting with the pointer, which is in turn interacting with the electron. Put all three of them together, treat the collection of the three of them as just another, albeit very, very complicated physical system to which this algorithm should apply. And unfortunately, when you do that, you get an even worse answer, okay? That I'm going to end up in this brain state which doesn't correspond to either seeing the needle point this way or seeing the needle point that way. Good. Bohr thinks, like I said, what I would call a reasonable scientific reaction to this. Okay, something's wrong with the algorithm. Let's do some tinkering and see if we can fix it up. This was not Bohr's reaction, okay? Bohr's reaction was this thought that you can just take everything and throw it into the physical system whose behavior you're going to analyze, okay, by means of this algorithm, this is a mistake, okay? The idea that you think that physics, that any physical theory is going to give you a picture of what's going on that's complete in that radical way, okay, and that it even includes you doing the experiment and so on and so forth, this is a deep mistake. It wasn't obvious in classical mechanics that it was a deep mistake. In classical mechanics, we saw no obstacle to telling this story. The passing elementary particle causes a spark in the spark chamber. The spark emits light. The light enters my eye. Causes excitations in my retina, causes excitations in my optic nerve, yada, yada, yada. You can tell the story right to the end, okay? Or at least there was no obvious obstacle to telling the story right to the end. Telling the story right to the end would be a mathematically very complicated job because your eye and your brain and so on are very complicated physical objects when you analyze them in terms of their elementary Newtonian particles. But in principle, it didn't seem like there was any reason why you can't tell a story all the way from the beginning to the end, okay? Bohr thinks that the lesson of quantum mechanics was that the very aspiration of physics to be able to tell a story like this from beginning to end was exposed by the development of quantum mechanics as naive, okay? As more than could reasonably be asked of a physical theory, okay? And he thought this amounted to the discovery of something very, very deep, okay? The way he put it was that before physics even gets started, before you're coming to apply your physical theory to a certain phenomenon or a certain object or so on and so forth, before that process even gets started, in order to get it off the ground, you need to divide the world, as it were, into subject and object, okay? You need to make a division of the world into the stuff that, as it were, is standing in front of your measuring apparatus and the stuff that's standing behind your measuring apparatus. And what you aspire to apply your algorithm to is only the stuff that's standing in front of the measuring apparatus, okay? And when the measurement takes place, that's when the application of the physics ends. The physics gives you probabilities for how this experiment is going to come out, but the idea that the fact of its coming out is also something that the physics can describe should be given up, okay? This is something that certainly, prior to quantum mechanics, physics was much more ambitious than that, okay? The thought was, there's nothing special about calling something a measuring instrument. That just characterizes it as a physical system with a particular structure, which you can analyze using the fundamental physical laws, just like you could analyze any other system. Bohr thought that the lesson to learn from quantum mechanics is that that's not right. There can't be a sort of theoretical physical description of the entirety of the universe, including whatever it is that you use to measure that universe, including your brain, so on and so forth. If you don't first put a cut, okay, and agree to to some convention about what the algorithm is going to be applied to, what stands on this side of the measuring apparatus and what stands on this side of the measuring apparatus, you can't even get started.